Hello everyone. I welcome you all for our workshop on quantum machine learning. In this workshop, we are going to learn about quantum quantum computing, quantum machine learning, its applications. Also, we are going to do the project by using quantum machine learning concepts and see how we can apply those fundamentals mathematical equation of quantum, their behavior, and how they are assisting machine learning. Because what we know so far is machine learning, that is subset of artificial intelligence, and we do have ml algorithms which we apply to perform prediction, classification, and other kind of task. We also know about deep learning, that is subset of machine learning, where we are going deep insights to find in data by using neural network. Now, what is quantum machine learning then? And what is quantum? First of all, we should understand what is quantum. Well, quantum is a smallest unit. Okay, smallest unit. That too in physics. Especially, I am talking about energy. Okay, so a smallest unit in physics is called as a quantum associated with energy. So, what is quantum physics? Well, it is study of these smallest units which are categorized as electron, proton, neutron, photon, whatever be the elementary particles are. These are called as elementary particles. And obviously, they are smallest. For example, in an atom, electron revolves in its energy level, isn't it? There is a nucleus where protons are or neutrons are present and electrons are revolving. Obviously, they are revolving in their energy state. That is what we study in quantum physics, because these particles do represent the energy levels possessed by them while rotating or revolving, let's say revolving. in their energy level. They do have a property. Okay, electrons, they represent negative, and proton represent positive. Neutrons are neutral in nature. Okay, charge, that's what we can say. So here the concern is about energy, what they possess. And the study is related to the energy of these particles only, which we later on called as state, energy state. And in our machine learning, we do have states as 0 or 1, either 0 or either 1, but not together. If any particle, any object is present, it can be represented by 0 or 1, depends upon the state in machine learning. But in quantum, there is a superposition of states. 0 and 1 can be present together also. How? Why? As I said, we are dealing with energy, we are dealing with small particles. These particles are present in some levels. They do have a state which can be both 0 and 1. 0 can be there, 1 can be there, both can be there. Now the question is, sir, how you are seeing? If I talk about light, we have studied in physics that light, according to Newton, show particle nature or behavior. Newton has given corpuscular theory where he told that in light we do have particles. There was one more theory where wave nature was shown. Therefore, the researchers, scientists, they told that light has a dual nature. That means it can behave as a particle, it can behave as a wave. Both is possible with light. Particle plus wave. That is the reason we are saying that energy, these particles which are present in some level, they can show dual nature. And because of the dual nature only, I am saying that 0 and 1 both can be present. In a general, machine learning do have either 0 or either 1, but we cannot have an answer both 0 and 1. But in quantum we can have an answer, we can have a state where both 0 and 1 can be present. Okay, that's what superposition means. And showing wave as a nature like this, we can have amplitude, we can have frequency, that is 1 upon time period, as the characteristics of waveform. And I hope you have seen the rippling. For example, when we drop a stone in the water, then there is a wave for form. Okay, the superposition of wave will be there. Okay, got it. Now, why this concept is important, why quantum keeps weightage nowadays, that we are building quantum computers and for calculation, complex calculation. I want to give one more example to you. For example, let us say you toss a coin. You are expecting at the end head or tail. Okay, that's what you are expecting. Either head will come, either tail will come. 50-50% chances is there for coming head or tail. So, sir, where we can apply quantum here? That means you told so far that either zero or either one is there. At one stage, you are saying in quantum zero and one both are there. So, sir, while tossing of a coin, where is both zero and one present? So, let me clear you this thing. When you toss a coin, it is in the air. So far neither we came to a conclusion that it will be zero or head or it will be one or tail. It is in the air, but still it comprises of both head and tail, zero and one with it. So we can, on the basis of this, tell both zero and one are present, because end conclusion probability, that will call as a probability end conclusion, head or tail. But what about when you have tossed the coin? What state you will define for tossing of a coin? It can be defined by quantum. Got it? Understood. That's why quantum keeps importance. All kind of possibilities can be covered under quantum. Let me share you my entire screen and make these much more simplified for you, because like in this workshop I will be stretching from basic concept to the advanced concept. Okay, so everything means to be clear for you all. Quantum, obviously, like a small unit. Okay, it's a small unit in physics. Possible unit, small possible unit, especially energy. Okay. In quantum physics, we do have electrons, photons, atoms, subatomic particles, I already told you, which possess energy, which rotate or revolve in their energy levels. Okay, fine. Quantization means discrete packets called as quanta. Discrete means countable in nature. Okay, therefore, you can tell here that quantization is a energy packets. Okay, energy packets, energy levels. That's what I'm calling as quanta. Electron in an atom can occupy a specific energy level. In chemistry, we define all those levels as 1s2, okay, 2s2, 3p6, if you remember. You studied in 11th and 12th standard. Also, here, wave particle duality, I already cleared you. Tiny particles can behave as sometime corpuscular or particle, or sometime wave also. Okay, light can act as a wave, also individual particles called as photons. Then, in a wave theory, we do have amplitude represented by y equal to a sine omega t plus xi. It represents the height of the wave. Larger the amplitude, more is the energy carried by the wave. Frequency is the number of complete wave cycles represented by 1 upon time period. It is measured in hertz. You very well know about it. This is how we show wave. Okay, amplitude, length of the wave, that means between the two crust. This is trough. This is crust. From here, the wave has been originated. Okay, if the gap between two crust is more, or trough is more, we'll say low frequency. If it is being a bit less, mid frequency, and, and if it is very less, then high frequency. High frequency, you can see more oscillations are present. This is high frequency, and your particles do oscillate in their energy levels. All right, we are talking about energy only in quantum. Quantum is much more related to energy. That's what we have studied so far. But that energy we are relating with the particles, because particles do possess those energy in their levels, in their state. Okay, long wavelength, short wavelength, and there is a formula between speed and the wave. V equal to frequency into lambda, where V is the wave speed, F is the frequency, lambda is the wavelength. And these formulas are not new formula. We have already studied in our schools only. Got it. In engineering physics also might be you have studied these formulas. Now, superposition of the wave. A quantum particle can exist in multiple possible states at the same time until it is measured. Until it is measured, there could be multiple possible states. That means 0 and 1 both can be present simultaneously. That's what I have told you about. When you have tossed the coin, right now, it is in the air, and because it is in the air, multiple possible states is there until it is measured. If you are measuring, that means like at the end, you are going to check when it fell down, you see what is the outcome. That is called as probability of getting head or a tail. But during its presence in the air, we are saying that multiple possible states are there. Therefore, 0 and 1 both simultaneously are present. We call them as qubit, quantum bit. Entanglement. This entanglement means two particles which are connected to each other can influence the state of one another, even if they are far apart from each other. So there could be influence in the particles also. One more thing I want to tell you: we have studied a very good principle in physics, uncertainty, Heisenberg's uncertainty principle. If you remember that, neither the position nor the momentum will be same, and this is the formula. If you remember, delta x into delta p is greater than h upon 2 pi. That's Heisenberg uncertainty principle. Position and momentum cannot both be known exactly at the same time, and in particle theory, this concept is being followed. Got it? Therefore, So far, we understood that particle energy multiple states are possible in quantum, and such concepts are used in building transistor, chips, laser, MRI scanners, solar cells, quantum computers, and quantum machine learning. That is what our concern is. Okay, so quantum computer can use qubits, which can be 0, 1, or both simultaneously because of superposition. Okay, this allows quantum computers to solve many problems. Okay, and in a faster than classical computers, because classical computers has to wait for a expected outcome. That's what I told, 0 or 1. But with multiple states, quantum can work. So quantum means very small scale energy matter behave in discrete units, follow spatial rules of everyday world problem. Okay, quantum computing. Well, computing is a technique to enhance hardware and software capability. Now, if you are dealing with a quantum and you are designing any system, so we need to enhance the capability of that system in terms of quantum. That means that system should use the qubits, 0 1 combination of both, can explore many possibilities simultaneously through quantum effect, energy levels, and that should be specialized in scientific and optimization problems. While classical computers, our machine, this machine, CPU, okay, it works on 0 and 1. This CPU machine doesn't works on like a superposition of bits. That's not happening. In quantum machines, there will be superposition. So qubit is this, what I told. It's fundamental unit of quantum property is called as superposition. Qubit representing multiple states. And the simple analogy I have already told you, a spinning coin is not clearly head or tail until it stops. Okay, so you have tossed a coin, or if you roll a dice, while rolling a dice, ultimately, if it haven't come to 1 to 6 between any of the number between 1 to 6, then it is having multiple states. Okay, so during that time period, who is going to define your action? Quantum can define, machine learning cannot. Okay, so a coin lying on a table can have head or tail. That is classical theory. While spinning of a coin or tossing of a coin until it stops, this is roughly an analogy for a qubit in superposition. That means one is also there, two is also there. If I'm talking about rolling of a dice, three is also there, four is there, five is there, six is there. A superposition of all. During that act, it may happen that 6 is having the highest probability and rest are having low probability during that time period. Or if you toss a coin during that time period, there might be 75% during that and 25% for coming tail. But you are talking at the end, head or tail. Okay, and then what about this entanglement? Two or more qubits can be linked together. When qubits are combined, the state of one is related to the another, enabling powerful computations. So we can combine two or more qubits. Okay. And inferencing means to amplify correct answers and reduce the incorrect ones. That is what is inference. Okay. Here, I'm not talking about only probability or amplitude, that means a particular value. I am talking about probability amplitude. Probability amplitudes. Therefore, in quantum mechanics, we represent a qubit in form of 0, 1, 0 plus 1. Okay, 0 plus 1. Subject to alpha and beta. These two are probability amplitude for state 0. This is state 0, this is state 1. State 0 and state 1. Probability amplitude. Okay, So these amplitudes are not probability themselves. They will become probability once you square and add them. Okay. Once you square their magnitude and add them, then they will become equal to 1. So this is qubit equation. Qubit equation. We are having 0, we are having 1, or we can have both 0 and 1. In case the value of alpha is 0, so the answer is 1. If beta is 0, then answer is 0. And if there's chances for both, which we are calculating here, let's say this is the probability alpha square plus beta square equal to 1, and alpha square root of 3 by 2, beta 1 by 2, will take the square, 75% chances for 0 and 25% chances for 1. That's what we mean. This measure the qubit. This is measurement of qubit. All right. So in quantum, we are having probability amplitude. And why we use these amplitudes instead of simple probability? Because we are talking about the superposition. Amplitudes can be negative or complex number, allowing quantum states to interfere with each other. Because superposition, entanglement, we want interference between these particles, these qubits. For example, if you are writing 1 by square root 2 0 state plus 1 by square root 2 1 state plus, okay, we can also write minus. And obviously, particle can have a positive spin, particle can have a negative spin also. And these are energy which you are representing in the particle by writing these qubits. We have to understand, if we have gone through in depth related to the particle theory, then we will understand that yes, positive negative spin can be there, energy levels where particles are present, we need to assign them some value. Okay, so how we are assigning them? Zero state, alpha and beta, calling them as probability amplitudes. Okay, so same probabilities when measured, but they have different during quantum computation because amplitudes can have a different sign. Depends upon the spin of a particle. Okay, so we require quantum computers because I guess many of the people are working on quantum, but still it's new to explore. You will not see many papers being published in this area, and whenever it comes to the research part, people work on ML, DL, problems like computer vision, text, and etc. etc. Quantum, because the point is. Because they told that we can have multiple states, complexity representing any data, multiple states will create a trouble. Why? If you're dealing with images resolution is 256, let's say 256, we can have so many features present in it. And when so many features are present in an image, and we require quantum to solve or to classify, then how many qubits will be there? It will be 2 to the power n. Okay, and it will take a long time to solve on your local machine, CPU. I'll let you know. Currently, like these are the applications: drug discovery, material design, etc. etc. You will read from your side. Okay, so the challenges is qubits are sensitive, require sophisticated error correction, and many quantum computers needed extremely low temperature. That means if you are dedicated towards quantum, then you require a quantum machine to solve a problem. Okay, building large scale quantum remains a difficult task. So quantum computing is a paradigm. We uses qubit superposition, entanglement, and inference to solve problems. Okay, then what is quantum machine learning? See, quantum machine learning is not like some different. In machine learning only, we are using concepts of quantum. Okay, uh, to write a specific set of quantum algorithm that simulate the behavior, flow, and concepts of ML using quantum hardware. Okay, so let's consider quantum hardware and use a specific set of quantum algorithms to simulate the behavior of machine learning algorithm. So what is present in machine learning algorithm? In machine learning algorithm, we are having parameters like weight and the bias. We are having an equation y equal to wx plus b. We are having loss, error. Okay, so like I want to simulate this parameter, this equation, these losses, optimization, all like you know about the optimizers. Okay, so I just want to simulate them and use on quantum hardware, quantum machine. That's what I want to do. Okay, fine. Now, if you want to simulate this classical ML on a quantum device, what we require? Let's go through an idea of variational quantum circuit. Variational quantum circuit. Let's design a circuit inspired from quantum machine learning. Variational quantum circuit. So, what is present in variational quantum circuit? They are also called as parameterized quantum circuit. Obviously, in machine learning also we do have the parameter as I told W and B, weight and the bias. So if you want to do or create a quantum machine learning or any algorithm, we should have a parameterized quantum circuit. Okay, where some of the gates are tunable. Obviously, we do tuning of weight and the bias in machine learning. Here also we are having parameter, quantum parameter. We need to tune them. Tuning means learning only. All right, tuning of a parameter means learning. Got it. So following the figure shown here. Okay, you can see a figure. U theta, U theta is present. That means it's a simple variational circuit with parameterized unitary gate and a tunable parameter. It's called as a unitary gate U and a parameter theta. Sir, what is this unitary gate, sir? U. It is a quantum gate whose operation depends on one or more parameters, adjustable parameters. For example, let's say angle. Instead of being fixed head-armored gate, I will let you know what is head-armored gate. The gate can be tuned during training or optimization. So we do have a gate, parameterized unitary gate in quantum circuit. And this gate operation depends upon parameter theta, which we call as angle, u theta, where u is operator, quantum gate, unitary operator, and theta is a tunable parameter. Since quantum operations must preserve probability, the gate must satisfy u theta conjugate u theta equal to I identity matrix. Okay, so this is a transpose. Okay, u theta transpose u theta should be an identity matrix. For example, we are going to take a rotation matrix cos theta by 2 I sin theta by 2 minus I sin theta by 2 cos theta by 2. So this gate rotates a qubit by an angle theta around x axis in a Bloch sphere. Rotation is happening about x axis. Similarly, rotation can happen about y axis. All right, qubit are rotated. That rotation operation is represented by u, and the parameter is theta, where we are going to put an angle value. It can be 0, means no rotation. There could be 90-degree rotation, there could be 180-degree rotation possible. So theta is tunable. Theta, this parameter is tunable. As I told, in our classical machine learning, we have Wx plus B. Here we are having U theta. Okay, theta we need to initialize and we need to run the quantum circuit. We need to compute the loss function and we need to update the theta using an optimizer, as the thing which we do in machine learning. Same we need to do here. So I hope you understood something. That sir, here is a function that is called as U unitary circuit. which is having a parameter theta, and this unitary circuit do follow a property which we have seen, that u theta transpose u theta is an identity matrix. Okay, and this u theta unitary circuit have an operation which we have defined here as rotation subject to x-axis or y-axis. And if you can see it properly, we do have I also, imaginary. If you see here, we do have imaginary I, because in complex numbers we have a plus ib. If you remember maths, any number can be represented in complex like a plus ib, okay, where I is the imaginary axis. All right, that is why we are seeing here in quantum that we are going to solve a complex problems which are having superposition. That is the reason, recheck the matrix of rotation cos theta by 2 minus I sin theta by 2. Then minus I sin theta by 2 cos theta by 2. So rotation about x axis. Similarly, we can have a rotation about y axis. Alright, and it's particle. It's rotating. Positive rotation, negative rotation by a certain angle. Okay, possessing the energy. That energy is qubit, 0, 1, or the superposition of both of them. Represented by an function u theta, and we need to optimize that function u theta just like machine learning we do. Okay, so like here, uh, the flow of quantum machine learning, what process we need to follow in order to solve it. Three things must be clear. Three things must be present: encode, process, and measure. This is what we need to follow in quantum machine learning. Now, listen carefully. ML, as I told, you do have y equal to wx plus b. You calculate a prediction. You perform y dash minus y as error. Then you optimize error. Del error by del theta. Theta is the parameter. Either it can be w, either it can be bias, weight, or a bias. And you write the update equation as w dash minus w alpha del l by del w. This is what you write. Similarly, for bias, you write beta or bias minus alpha del l by del bias. That is what you write. We need to catch up the same equation for quantum, but the point is function is changed. Instead of this wx plus b, we are having u theta, we are having unitary circuit. Okay, now initially you are not given that this is a quantum bit. Okay, if you have been given with a classical value, you need to encode it first to convert it into quantum. Then only you can work on a quantum circuit. Now, classical bit will not work on quantum circuit. You need to encode it into quantum qubits. Then you will give these qubits as an input to the quantum circuit. So here, that concept only is present. Encode, process, and measure. Step number one, encoding. As we are dealing with quantum computer, classical data cannot be solved on a quantum device. We need to encode it according to the quantum nature. Okay, several methods are applied. For example, basis encoding, amplitude encoding, angle encoding, higher encoding. There are so many things we need to do. We need to do encoding. Processing. Then once you give this encoding into the quantum circuit, you need to process this input. So variational circuit is applied that will adjust the parameter. This step will be repeated by optimizing the parameter theta. How weights are trained in classical model, and similarly that theta will be optimized here in the process. Then measuring. We want to extract the results of our model processing in interpretable format. This can be done using several methods and applying them repeatedly, known as the number of shots, where each shot the quantum state collapse into one classical state to get a probability distribution. So remember, We need to measure the results. You have converted your input into encoding qubits. You have given the qubits to quantum circuit. Quantum circuit is processing your qubits. Now, after processing, it will give a result. You need to measure them. That what result came. So, how the measurement can be done? They told that measurement can be done according to the number of shots, where each shot is a quantum state collapsing to one and only one classical state. Quantum will collapse and it will give you either 0 or either 1. This is called as measuring. Okay. This is called as measuring. It will collapse. Got it? More mathematical perspective I have mentioned ahead in the template, like representing x into xi x quantum. Okay. Basis can be encoded, amplitude, angle, all can be encoded. Then after that, you need this is angle encoding. Okay. For example, if a feature x is present, you can encode it through a rotation gate. This is angle encoding, rotation gate. Fine. Either x or either y, you can take. Then we need to process this quantum this using quantum circuit, this encoding. Okay, it is represented as after encoding the quantum state is processed by variational circuit. This is how we need to do u theta, and this is your input quantum input or qubit. Okay, where theta is a trainable parameter. All right. So theta randomly we initialize, run it over the circuit, and loss is computed, optimized, and minimized. Minimization will be done. In measurement, we will convert quantum to classical again. So the final quantum state cannot be directly interpreted. No, it's not possible. At the end, you need to again convert them into classical. So during measurement, this is quantum, we need to convert it into either 0 or either 1. Okay, that's what we are calling as shots. Okay, so the quantum state collapse into classical state because quantum measurements are probabilistic. A single measurement is usually inefficient. Instead, the circuit is executed multiple times. These repeated executions are called as shots. For example, if you run a circuit 1000 times and you are getting 0 as a result in 700 and 1 as a result in 300, so probability of 0 will be zero point 0.7, probability of 1 will be 30%. So these probabilities can be used to determine the predicted output y cap or the prediction, because probability of 0 is coming 70%, 70 times. So according to classical concept, we will say that the prediction is 0. You have run the circuit 1000 times, 700 times you got 0, 300 times you got 1. According to the probability, this is 70%, this is 30%. I require only one answer as classical theory. So let's go with the highest probability. Therefore, the answer will be 0. Answer will be 1. Okay, so we can optimize this variational unitary by this is prediction, this is actual error, ka square, average error, mean square error. So n is the number of training samples, y dash is the prediction, y is the correct. This is not a new thing. I already mentioned you here in yeah, here it is. Error, y dash minus. That's the same thing they are mentioning. Okay, and we do focus upon mean square error. So y dash minus y ka square. This is square. This is the summation. Here we are going to take the mean and we call it as MSE, mean square error. And we do perform the optimization of this error only by doing differentiation, partial differentiation. So this error, MSE, I am taking the differentiation. That's what we call as optimization. So in quantum circuit also we need to do the same kind of optimization. Okay. Now, fine, I guess these things are clear. Update equation, I've already mentioned. So what we did, this is a parameterized quantum circuit. We have given input quantum qubits, input processing has been done, cost function evaluated. There is a we are using classical optimizer. We are using classical optimizer. For example, Atom. Okay, classical optimizer to optimize our results to reduce the loss. Okay, not any quantum optimizer. We are using classical optimizer. That's what you know. Atom. Or there are other optimizers also. We can take SGD, Momentum, Nestrov. Atom is the best. Okay. So quantum machine learning optimization, there is no classical weight W. We are having variational parameter theta. We converted our x into xi x. We are given xi x into u theta, which is your quantum equation. Then we are optimizing this quantum equation in a variational circuit. This one, parameterized quantum circuit, here we are optimizing. Okay, equations are just like same. No change in the equation. You can see all these updates are clear, same as machine learning. So hybrid quantum classical optimization, what steps we are following? Input data, quantum encoding, variational circuit, measurement means drop, drop, that means fall of quantum to classical, getting the prediction. Once you got the prediction, calculate the error or the loss or the cost function, then use classical optimizer, that is Adam, to optimize the loss, reduce the error, update the value of theta, and again run the circuit. So while running the circuit, you will get quantum results. Okay. While measuring, we convert quantum to classical, and then we follow machine learning. So this is hybrid. This is hybrid architecture. Till here, quantum is present. Then machine learning is present. Here, machine learning is present. Okay, and then again, circuit is running. Quantum will work. Okay, got it. So unlike classical neural networks, standard backpropagation cannot directly pass through the quantum measurement. It will be complicated. It's complicated. So common approach is parameter shift rule, theta plus pi by 2 minus theta minus pi by 2 divided by 2. This is c theta, delta c by delta theta. This estimate how changing parameter affect the cost function. So this is an optimization equation, parameter shift equation. Okay, and like we can use these optimizers to solve this equation. Okay, got it. Fine. Therefore, we understood by the basics of quantum that that entire quantum theory relates with energy. Energy, if I need to define, I require particles. Particles I am taking small, they do have states, depends upon their spin, they can have positive, they can have negative, and and 0 1 superposition of 0 and 1 can also be present. They can influence each other also. All right. Therefore, what to do? We will take an input, give it to quantum function that will convert this quantum into qubits. We are calling it as U, where there is a rotatory circuit which will rotate your input and convert it into quantum. Then we can use this variational circuit to perform computation that we'll see in the coding just now. Then we are going to measure it. For measurement, we will convert this quantum results into classical ones, 0 or 1. Then after we are going to do the prediction, and prediction we are after prediction we are going to calculate the loss or the error, and then we can optimize the loss. and then we can rerun the circuit. Rerun the circuit. This is hybrid model, quantum machine learning. And for your convenience, let's get started with the coding to do the implementation part. Okay, I have already shared the notebook with everyone. I hope my screen is visible. You can see QML tutorial. Here you can see the QML tutorial, quantum machine learning tutorial. Notebook is available. Let me reshare it again, and you can run it at your end. Okay, here you can run it. Please open the notebook, and you can do one thing. You can copy and edit my notebook. Once you open my notebook, you can copy and edit and run all those cells. Now, since we are dealing with quantum ML, so general machine learning libraries are not enough, because they already told you need to convert your input into qubits. So, converting input into qubits, you require quantum library. So, what kind of libraries are present with you for that particular conversion? Therefore, there is a library called as Penny Lane. This is a library, Penny Lane. All right, Penny Lane is a cross-platform Python library for quantum computing, quantum machine learning, and quantum chemistry. Train a quantum computer with the same way as a neural network by using this Penny Lane library. So before using this library, you need to install this library, and here is the installation package. Pip install Penny Lane. Further details you can go through from here. Let me share you this website. Okay, here in the comments you can open this website and keep it as for your reference. Okay, let me come to the code here. What I did, once you create a Kaggle notebook na, this part of code will be there. Okay, this part of the code will be available. Next, what you need to do is pip install Pennyline. So I request everyone mandatory to kindly work on the notebook which I have shared. The first thing which you need to do is pip install Penny. Okay, install this library. It will be installing quickly, not take much time. Pip install Penny. Okay, because we require a support for quantum computing. Currently I don't have any machine quantum where I can do this activity. Therefore we are simulating, we are having an environment where we can create a quantum circuit using these libraries. All right, fine. So pip install Penny Lane, and after installing Penny Lane, where this is the first part of the code which we are going to perform, creating a single qubit and measuring it. Okay, let us create a single qubit and measure it. Measure means convert that qubit into classical machine learning. A very simple code. What we are going to do is import Penny Lane as QML and take a quantum device where you are having only one wire, one circuit is there, one wire is there. Okay, one wire. And then you are creating a quantum node and defining the state, and then you are running the circuit. All right, fine. So here is the explanation of each and every line of the code which I have done. First is device creation. Obviously, I require quantum device to convert input into quantum bits. So this will create a quantum simulator with one qubit. One qubit. It will create a quantum simulator, quantum environment of one qubit. Then quantum node will be created, and that will convert Python function into quantum circuit. So this is the node, and I'm going to convert this node into quantum circuit. So I have made a Python function def circuit and return qml dot state. So what does it mean? It means that convert a Python function into quantum circuit, and later on, measure we need to measure the state in classical. So return qml dot state. That is what we need to measure. Okay, state measurement return. What it will return, what it will give, it will return the quantum state vector, like 1 plus 0 j, 0 plus 0 j. This means that the qubit is initially in 0 state. Okay. You can run this code, and this is what you are going to get as a result: 1 plus 0j, 0 plus 0j. This 1 plus 0j, if you remember, 1 is the real part, 0 is the imaginary part here. And here also, 0 is the real part, and 0 is the imaginary part. Alright, so what we did in this particular code, we are using penny lane, we are defining a quantum device. Then we want to create a circuit, quantum circuit, and then we need to run the circuit. And while running the circuit, we got the result as qubit. Okay, we got a result as qubit. Fine. Got it. This is what we are getting as a result. Alright, it went up and down. Okay, I hope you understood how to make a single qubit and how to measure it. So we have created one single qubit and we have measured it. Second is second is applying Hadamard gate. Hadamard gate. So what is this Hadamard gate? Let me explain you some concepts of Hadamard also. This is Hadamard. Hadamard gate or a rotation gate. Like there could be different gates which we are calling as U or unitary circuit. Fine. So Hadamard gate is one of the most important quantum gates in quantum computing and quantum machine learning. It creates superposition, allowing qubit to exist in multiple states. So if we want a qubit to exist in multiple states, we need to pass this through certain gate. Then only it will follow the superposition. So if you have any question in your mind, sir, previously you took cos theta, sin theta. That means you have you took a rotation gate, x rotation, y rotation. So why you have taken? The point is we need to perform superposition. We want our uh, qubit to be present in multiple states. That is why we have taken the superposition. Alright, so Hadamard gate represented as h equal to 1 by square root 1 minus 1. This is Hadamard gate. Okay, so action on the basis states, like if I apply h on 0, if I apply h on 0, h0. Okay, so it is represented as 0 plus 1 by square root of 2. And if I apply on 1, then it will be 0 minus 1 by square root of 2. So remember one thing. You see, positive is for 0. That means we are creating an equal probability of measuring 0 or 1. And you can see 0, positive for 0. And if I apply on 1, this is negative. All right. If you check the code number one, if you check the code number one, we are getting 1 plus 0j and 0 plus 0j. That is why here they have mentioned this means that the qubit is initially in 0. Why they told? You haven't asked me the question why. Why it is in 0 state? Because you can see the results are plus. So it is in a 0 state. If it would be minus, then it will be in a minus state. Okay, and if we apply Hadamard, then we can have a superposition. Okay, we can have a superposition. Let's say before Hadamard, 0 is, this state is having 1 and 0, 1 and 0 values. After Hadamard, it will be 1 by root 2, 1, 1. Probability of measuring 0 state is 50%, and probability of measuring state 1 is also 50%. So after Hadamard applying, I got this. Before Hadamard applying, I am having 1 and 0. So we need to apply Hadamard, put the value of of 0 in the equation, we will be getting it. we'll be finding it. All right, so the result came as 1 by square root to 1 1. This is a simple explanation they have mentioned, given or given.
Hello, sir.
Yeah, yeah, please.
Sir, like you define a circuit in the code.
Huh?
So this circuit is related to the circuit that we study in electronics, or it is just a
It's
name?
like electronic only. If I show you, it's kind of electronic circuit only. It looks like that. For example, let me show you. Check here, like this. Okay, like this. So we are having the bits: first bit, second bit, third bit, fourth bit, or let's say 0 bit, 1 bit, 2 bit, 3 bit. We are going to convert them into quantum bits, qubits, and then we are having a rotation. Rotation is your function, psi function, or either you can take Hadamard function, or either you can take rotation function. This will create superposition. This will create superposition, and you can add layers. For example, this is a circuit. We are having this thing at layer number 1, layer number 2, and here is the output, which you can measure later on. Okay, got it. And you can see the interconnection
Yes.
between these bits. These are the interconnection. Okay, or superposition. Let's say we are having the superposition. That is why they told that in quantum we are having superposition, because of this rotation you have followed. So conversion, rotation, as a quantum circuit having superposition, later on you can measure. So such
And
kind of circuits.
finally, we get the output like zero or one.
Output 0 or 1. Output you will get 0 or 1.
Okay, sir.
All right, fine. We are not preparing any optimizer which is quantum optimizer. Okay, multiple states optimization, it's never been easy. All right, either 0 or 1 we can optimize. Multiple state optimization is not easy. All right, I'm going to show you this code. We'll run this thing. All right, so first we have created. Second, let's say, I was talking about header mod, na? I was talking about header mod gate. This code, run the cell number 2, where we are taking header mod. Okay, so that will create a superposition. Transform 0 to 2. Okay, it will transform 0 to 2. Probability measurement returns the probability 50-50%. That's what they also mentioned here. They also mentioned here in Hadamard that the probability will be 50-50%. And why Hadamard? Let me explain you this thing also. Most quantum machine learning algorithms start by placing qubits in superposition. Without Hadamard, 0 is only one state. With Hadamard, it will be having multiple states, multiple possibilities. So if I put 0 into the Hadamard, I will be getting like this: 0 plus 1 divided by square root. This is what I'm going to get. This quantum circuit now process multiple possibilities. Multiple possibilities are there. If we are having only 0, one state. Passing only 0 into Hadamard, we can have multiple possible states. Okay, applications are variational quantum circuits. That's what we are making. That's what we are designing. Okay, got it. So, what is Hadamard? Hadamard is a quantum gate. It's a method. It's a function. It's a quantum function for superposition, for creating superposition. That means for creating multiple states for a single input. Okay, creating for multiple states for single input. All right. So this is your Hadamard function. Okay, you have applied Hadamard on 0, so you got this thing. 0 is one state. 1 is one state. If I applied 0 to Hadamard, I am getting 0 plus 1 by square root of 2. That means this create equal probability for both 0 and 1. That is why they are saying 2. Equal probability for both 0 and 1. Alright, got it. So if let's say 0 is 1 and 0, now passing it into Hadamard, it will create 1 by root 2 1 1. Where there is a chance of 0 state 50%, 1 state is also 50%. That's what mentioned here in my notebook also. Okay, 50% chances of measuring 0 and 1. That's what you got. Once you run this code, na, you will get it. Alright, let me add almost. Alright, fine. Now, next. Rotation gate. Okay, change the gate. Instead of head hammered, take the rotation gate. Still, we are having 50-50% chances. Still, the output is 50-50% chances only. What I did in this particular code, I'm taking penny lane, I'm taking numpy, I'm defining the quantum circuit. Okay, quantum bit. That means where I need to uh, run this function. Okay, quantum circuit. So I require a quantum device. So default qubit wire equal to 1. Okay, and this is my device. In general, either we take CPU or GPU, but here there is no CPU, there is no GPU. We are simulating an environment where we are having a quantum machine, let's say. All right, so that is why the device is quantum circuit, quantum device. Okay, create a node, and in this node you need to define a circuit where wires are present, and they are going to create superposition. So take a rotation as a function, as a unitary function. Take rotation. Above we took head hammered, now we are taking rotation. All right, theta is the parameter. Theta is a parameter. You are passing 0 as an input in the wire. Okay, and then later on you are calculating the probability for 0. So you are inputting 0 in the wire as an input, and then once it passed through the rotation circuit, rotation QML, you are going to get the results for that, and there will be 50-50% chances. As like above, here also you are getting 50-50% chances. So I am explaining you the very easy and the basic codes, and I guess nowhere I think this is present. I hope you run that code also. Not 2 bit, 2 bit. Okay, previously you are passing either 0 or 1. You pass 1 0. Okay. Now I am taking again define to take two wire. One wire for 0, one wire for 1. So take two wire for input. Okay, define your quantum environment. Then create a node. In this particular node, define a circuit. And you are taking head hammered. You are passing head hammered. 0 you are passing to head hammered. And 0 and 1 you are passing to C naught. This is also one of the function. So there could be many function for superposition. Na? Above you have seen head hammered, rotation. Here you are also seeing the complementary of not function, C not function. Find the probability of the wires 0 and 1. They will let you know. Point 0.5, 0, 0, zero point 0.5. That is the probability coming. So wire 0, it will create two states, 0 1. Step number 2, we are taking C naught for 0 and 1. It will entangle two qubits. That means it will superimpose two qubits. Result into Bell state 0011, and the output is 0.500. And the probability is 50%, 0%, okay, 0%, and like 50%. That is what the result is coming. All right, so you have given 0 and 1. It has converted into 000110 and 11. And later on, it has also gave the probability of all these results. Like what is for 00 and what is for 11 and what is for the rest. Here is a code which you can perform. 2 qubit interment. Understood. Simple variational quantum circuit also, you can run this code, and it's like same only. I'm taking node, quantum node. Okay, obviously penny lane library, numpy. I am taking numerical Python to do some maths if it's required. Okay, node I have defined, circuit I have defined inside the node. I am taking header mod, and wire 0 I am taking input as 0. Then I need to return the state, and the answers are coming to be as point 0.7, point 0.7 plus 0j, 0.70 plus 0j. That means what we are doing, we are taking a trainable parameter theta, that will act as a neural network weight. Okay, And are we passing here into rotational circuit? I guess no, we are not passing into a rotational circuit. We pass it into variational circuit. Anyways, here is an example which we can follow, like passing it into rotational circuit or Hadamard circuit, let's say. After parameterization, we can measure them, and we can expect the values whatever it will give after the measurement, and that's what we are displaying in terms of probability. All right, so that's one of the code related to variational quantum circuit. All right, let me simplify so far what we have done, because next will be a project kind of stuff. Next will be a project kind of stuff. Before that, before moving, let me explain it. We are taking Penny Lane library for quantum. Then we needed to create a device, a quantum device, over which I can run my circuit. So after creating a device, I am creating a node. In this particular node, I am creating a circuit. In this circuit, I am taking Hadamard as a unitary function. Okay, unitary function. Or I can take a rotation as a unitary function, or I can take a c naught as a unitary function. You have to study, there are so many functions available in quantum, you can go through them. Okay, so I need to take a unitary function. In this unitary function u, I need to take a parameter theta. Okay, so what I'm going to do here is, I am taking a input 0. Let's say I am having a wire 0. I'm taking input 0 into the wire 0, and I'm passing this into the unitary function, and then I am returning the measurement. That is what I'm doing. Measurement, return, and print the measurement. That's what I'm doing. So far we have performed this code only. If you check, we have performed these codes only. Here also, q state. Okay. Either return the probability or either return the state. So probability return. Probability return. Okay. Here also probability return. But in this code I am returning the state and printing it. Okay. So either you can return the probability or either you can return the state. It will let you know how much it comprises of. Okay. So here are the probabilities. 50-50%. And here are the states. Any of them you can return. Okay, got it. You can try these codes. I expect everyone has done. Now, what next? I'm making. Let's take some complicated problem statement. Okay, yes, set it out. Please let me know. We are retrying. Okay, retry, correct, none. Is this a warning? Mr. Venkat, you can ignore the warning. Not an issue. Warning is not our concern. You can ignore the warning. If error comes, then we'll check. Warning is something which came during execution, so ignore the warning. Okay, so here is our next entire code demonstration. What I'm doing is, import penny lane. From penny lane, take numpy, then take an optimizer Nestro. This is like classical optimizer. Okay, Nestro momentum optimizer. Nestro is classical optimizer. All right. Then take matplotlib for plotting. All these basic libraries I am taking. Then obviously I am defining the qubit device, quantum device. Okay, where I am taking 4 wire. You have to take 4 wires. Previously you are taking 1 wire or you are taking 2 wire. Here you are taking 4 wire. Okay. All right. That means you are interested in supplying four digits, 4 units. One, two, three, four. There are four wires as an input. Zero, one, two, three. That's what you are expected to give as an input into the quantum circuit. All right. So four wires are defined. Then state preparation. State preparation. Okay, like what it can be state zero, one, two, three. These are the states. We are going to give it into the wire. Define the layers. Okay, how many layers are there? We need to take a rotation function. We need to take a C naught function where they will be in a combination. Okay, and four layers are being defined here for wire in range four. Wire in range four. Four wires are there, na? Four wires are there. So in a layer, every wire every wire will get its respective value. Here in rotation we will give 0, then 1, then 2, then 3. In a C naught we will give 0, 1, 1, 2, 2, 3, 3, 0. Okay, so that's what we are defining a layer, and such kind of input we are going to give. After that, we are going to create a variational classifier without a bias. So state preparation, define weights, assign weights, and return exp exponential value. What actually we are trying to do? Parameter building. Parameter building, because here you will take the input, but you need to optimize the parameters. So input will be x, but your parameter will be weight or bias. Both also can be there, and the optimization required for that. Therefore, we are creating a random weights here, random parameters here. That's what we call it as theta. So random weights are created. Okay. Similarly, bias also. Okay, here they are taking without bias. Without bias, this is without bias. Okay, so bias has not been there, but the initial equation is wx plus b. X is the input weight, w bias b. That's what happens in our machine learning equation. All right, so similarly we are trying to create our parametric equation from this wx plus b. Two layers we are taking, and the weights will be assigned randomly. Bias will be 0. Here we are taking bias 0. Two layers, and one every layer have this thing. Every layer is having such many wires present in it. This much wires will be there. Two layers we are going to take, and the parameters weight and the bias will be like this. Okay, got it. Then this is how your circuit looks. Drawer, qml dot draw mpl. This is how your circuit looks. So this is layer number 1, this is layer number 2, and we are having rotations present in it. Okay, rotatory circuit, four inputs you are already given. This is your quantum function which will convert them into superposition quantum bits. Then only you are going to perform the rest of the task. All right, and you are giving weights and input as 0011. Drawer weights 0011 without bias. Here is a circuit prepared, two layer circuit. This is two layer circuit. Okay, got it. So you can make a plot also for variational classifier without bias. After that, calculating the accuracy of prediction. So accuracy is the total true labels divided by total. total number of outcomes. So that will be the accuracy. So here we can have a true labels, predictions, and we can formalize it. It's easy. We can also find the predictions variational classifier cost, that means error. This is error. It's clearly understood. What is cost? True label minus prediction, cost square, that is the cost. Okay, we return the cost, and cost is the error. Take Nestro optimizer. We already imported. Either you can take Adam, either you can take Nestro, or any other momentum. There are different as optimizers. So to take Nestro optimizer, here is your input. This is the training data. This is the testing data. All right. Then after training and the testing, you organize your data, and you are going to give this as an input to the variational circuit, the quantum circuit which you have prepared about. 5 batch size you are taking, 100 times you need to iterate, 100 times you need to train your circuit, train your model. So here I'm taking iteration 100. All right. And yes, fine. After training after training you need to optimize the loss, and that optimization of the loss will be done with the help of Nestro optimizer. Whatever be the predictions you are going to get, you need to convert them into measurements. Okay, then only loss will be calculated. Fine. So current cost, accuracy, and append, that means print. So here I am printing. Here I am doing. After 100 iterations, I am getting accuracy 100% for prediction. See how it goes. How it goes: 50%, 50%, 50%, then 60%, then 40%, then 50%, then 60%. At one stage, 40%, then 80%. That means jumping. The accuracy is jumping. Okay, fine. And then at the end, I am getting 100% accuracy. I made the plots here. Here is the plot: training and the training cost, training accuracy. There is so much fluctuation in machine learning. We haven't seen that much fluctuation. Machine learning doesn't happens such kind of fluctuation, but in quantum circuit there will be fluctuations. Sometimes 50%, sometimes 80%, sometimes 40%, sometimes 30%, sometimes 100%. So fluctuation at the end, I'm getting 100%. All right, fine. And here I have displayed the prediction from my model. The input is 0, 0, 0, 0. The output should be -1. Model predicted -1, 100% correct. Input is 0, 0, 1, 1. True is -1. Prediction is -1, 100% correct. So all the results are 100% correct. My accuracy is 100% for the quantum what I need. So what I did in a very simple way, in a very simplified way, what I did, as you have seen, as you have seen that four inputs are possible. I need to convert them into superposition quantum. Then I need to pass them. There are two layers actually. Two layers. This is layer number one. This is layer number two. As we make in deep learning now, we make a layered architecture in deep learning. Here also we are making two layered architecture in quantum machine learning. All right, and you can see there's a tapping. There's a tapping. This is what you can see. So one state can influence the another state. That's what we can see. And these are rotatory circuit: rotation, 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 rotatory circuit. Rotation. What is the rotatory circuit? You know, cos theta minus sine theta cos theta. This is the rotation. Rotatory circuit. Theta is a parameter, and we are optimizing, trying to optimize this parameter only. All right. So once we train this circuit, we got some output. Later on, you have measured it. You have measured it. So whatever be the probability of outcome came, we have finalized. We have finalized. Then gave it to the optimizer to minimize the cost or to minimize the loss. That is what we have done here. Okay. Got it. I do have the entire explanation, though I have explained you from here, but I will share you the document or template from where you can again revise what I explained. Anyways, okay, got it. This is my architecture, two-layer architecture or quantum circuit. Okay, in one go only, this code, this one, in one slot only I have created. Previously I did in different, and here I have done in one slot. Still, you are going to get the same result, 100% accuracy. Now, what I did, sir, in machine learning, we do have certain problem statements. Let's solve the basic problem statement. Everyone, please check this code. Erase data set. Erase data set. Everyone, please come to this particular code. Erase. Erase is a flower data set. It is having three output, four features, four training features. Target is having type of a flower, Setosa versicolor virginica. It's a multi-classification problem. And the features are sepal length, sepal width, petal width. Four features are there, and target is type of a flower, iris. So if you want to try quantum machine learning, you should be knowing how to design a basic code at least first. So what I'm doing is I help you in making the basic code from this tutorial. And now I am applying to a primary project. Let's say Iris classification. Everyone, please. Penny Lane, NumPy, Nestro, Iris dataset I'm loading. Train test split, obviously, I need to split the data into training, testing, and all. Min max scaler, I need to scale my data. And this thing, yesterday also I'm teaching to my training participants that we need to scale the data. So here we are having Iris data set. Iris data set is having four feature, length, width, and we need to scale them. So that is why I'm taking min max scaler. See, remember, there are different types of scaling techniques: standard scalar, min max scalar, robust scalar. Okay, min max scalar scale the values between 0 to 1. Okay, min max scalar scale the values between 0 to 1. So here I'm taking min max scalar. Okay, define a circuit that is quantum environment. Take the device, quantum device. Two wire, two wire I am taking. Okay, data I have loaded, x and y is there, and here I am doing a mask y less than 2, y less than 2, whatever be the y output less than 2. X mask, y mask, y equal to y square minus 1. So, like it's related to 0 and 1 as an output. That's what I'm. Listen, what I'm expecting. Y less than 2 and x equal to x mask. How many features I told you? In this data set, there are four features. There are four features in the data set. One, two, three, four, and a target. This is target. Sepal length, sepal width, petal length, petal width, and target. Setosa, versicolor, and virginica. Three classes are there. What I'm taking here is what I'm taking here. Any value of y less than 2 can be 0, can be 1. Okay. X mask, that means take one feature, take one feature of x and take one y target. Take one feature and take target. Y is y square minus 1. Y square minus 1. What is y? If you take less than 2, let's say 1. 1 square is 1. 1 minus 1 is 0. So let's consider only one feature. One more thing I just want to consider and clear you. Number of features are more, then circuit will be complex. We in the starting only I told in the start, because it will create 2 to the power n qubits superposition. If you are having 100 features or like, then there will be 200 something will be there. This much circuit is complicated. That's the reason what we do, we in quantum, just like we do in image classification task, now like image given to convolution neural network, and then neural like we perform classification. Here we don't do. We give, let's say, image to convolution for feature extraction, then we give it to PCA, principal component analysis, for dimensionality reduction. Anyhow we need to reduce the dimension. That is mandatory. We cannot give the entire feature to the quantum. It will take lot of time to solve. That's the reason we are taking a subset. We are scaling our x. We are scaling our x, aligning our x, converting it into numpy array, dividing it into train test, then creating our quantum circuit. Take all the features. Two wires are there, which will take 0 and 1 as an input. Okay. Define a layer, define a layer, perform rotation of 0, 1, 2. Why? Setosa, versicolor, virginica. Three classes. Total number of layers I am taking here is 3. Input I will take 0 and 1. Created a variational circuit, that means defining the weight without bias. Define the weights without bias, as we did above. Define the accuracy, as we did above. Define the cost. What is the cost? Again, label minus prediction ka square, mean average error. Alright, error we have defined above in the basic. Same I am doing here. Okay. Initialize random weights first. So this is random weights initialization. Bias will be 0 initially. Optimizer will be Nestrov, same. We have taken above. Batch size of the data will be 10. Okay. We will calculate the cost, error, and the accuracy. 100 times I need to iterate my circuit. We have done above, same. And here, that's what we are taking. That's what we are taking. Batch, any random values we are taking, selecting for training, random batch. Okay, picking that from X and Y, optimizing them with weight and the bias, WX plus B, getting the prediction from the variational classifier, calculating the cost, calculating the accuracy, and appending it into the empty list which we have created previously. Here are the figures which I have plotted after training, so you can see. For Eries data set, if you run this code, it will run quickly. It will not take much time, and in a very quickly we reach to 98% accuracy in 100 repos. This is one of the best code which you can learn initially by taking a very simple data set of machine learning. 98% accuracy, and all the predictions are nearly correct. All predictions are nearly correct. Maybe all correct, because the test accuracy is coming to be 100%. And that's the circuit which you have prepared. Two input. Last time you took four input. Now you are having two input. 0 and 1. Superposition, rotational. How many layers? Three layers, I guess. If you remember. Three layers are there. Layer number 1, layer number 2, layer number 3. Three layers. Okay, got it. We have defined the three layers. Okay. Yes. Yes.
Yes,
Sir,
sir. Here we are taking the four
uh,
features as a input, na?
how much four? Madam, four
Four.
we take features are four, but you remember what I'm doing here? If you check in the code, I already told above. Check here in the starting only. What this means? Y less than 2. S marks. What is X? X is your data having number of features. Having number of features. How many features are there? 4. But how much I am taking? Y less than 2. Less than 2 means how much? 1. So one feature, one target. If I take all, no madam, that is why I mentioned circuit will be complex. It will increase. That's why we follow dimensionality reduction, less number of feature. And I just want to remind those people who are working on quantum machine learning and if they are and they're trying to solve any problem or any classification problem taking huge number of images and size of the images is more as I mentioned 250 256. You cannot work on that much size of the image. No, anyhow you need to reduce the size of the image or you need to reduce the number of features by applying machine learning techniques, then give it to the quantum circuit. Before that, no, as it would take, I don't know how many days to solve. One feature is taken out of four. Yes, mask, that's what we are doing. And any of the feature can be selected. Any of the feature can be selected. All right, it's all random like selection. We can take sepal length and sepal width like this.
So this is user defined or
That
they,
we did from our side, madam. Here
okay.
we have defined from our side that take a feature. Okay, take a feature, do this kind of stuff, and then train a classifier, quantum classifier. Okay, but what is random here? Batch size is random. Any of the value will come. That is random. Okay, weight are also random. Bias we have assigned zero. Okay, predictions will depend upon the sign. What kind of sign it's coming? Okay, after rotational circuit, after rotational. Okay, because we are defining variational classifier. Okay, through a layered architecture, then calculating the cost or the error, calculating the accuracy. That's it. Your circuit will be trained, and that's what the result you are getting.
Sir, with one feature, it is giving so much accuracy.
Huh? With how
With
much?
one feature, it is giving so much accuracy.
This much accuracy. We got it.
With by selecting only one feature.
Here we have taken. No? That's what we have taken. Understand this feature. Only this feature. This much. And this much accuracy we are getting. Wire we are creating two. Two wires we are creating. Zero and one take as an input. Okay, creating a quantum environment with two wires, taking 0 and 1 as an input. Okay,
But
and here you can see X is there, Y is there, X wire 0 and 1, wire are 0 and 1. What we are going to take? Output is 0, 1 and 2. Output is 0, 1 and 2. Sitosa versicolor virginica. That's why 0, 1 and 2. That is the output, which we can expect from the input. We give an input with this is what we can expect from as an output. Okay, got it. So the input are zero and one. Okay, output are these after rotation. That's what the circuit is learning. From where the circuit is learning, and total three layers. Total three layers, and this is for every wire we have created. This is for every wire created. Wire number 0, rotation. Wire number 1, rotation. And this is for 3 times, because there are total 3 layers. And you can see here, for 0, for 1, 3 times, 3 layers. That's the architecture.
Yes, sir. Again, having a one question. So this is also a black box, like a machine learning,
Looking like a black box. Yes, looking like
because
a
which
black box.
feature is going to consider, we are not knowing that out
Well,
of the.
madam, it will be like a subject to explainable AI. So far, we are already finding difficulty in superposition in quantum. Then how we are going to introduce explainability? That which feature will result, because uh, we are applying quantum in circuitry level. After measurement, it will come into optimizer. That is machine learning. So, if
Yes.
something we can do, and one more thing, after applying quantum, we will ask, kindly give us probability or kindly give us the state. If it will give you the state, it will clearly mention answer is 0 or answer is 1. But if you're asking for probability, then it will give a 70% or 20 or 30%. It will. All right. Now, what made this circuit to give answer 0? That will, under the superposition, what happened? If we can try something that can be done at level, which level? Machine learning level, optimizer level. We can try from there. Here trying, I think I haven't also explored what made to give it answer 0 or 1. That is
So
explainable.
in these two wires, the two inputs are going on.
Yes, two wires. Yes, two wires we are taking.
So it means two features we will take.
So if you take okay, you are saying two features we are taking. All right. How you can define these two features then? Okay, I've gone above, but here only we'll check two features how we are going to define. That means you are saying one feature is 0, one feature is 1. That's what you are saying. That's what you are trying to say. One feature is 0, one feature is 1.
Yes, sir.
Well, 2 stands for bits. Taken a 2 stands for bit. If it's 4, na, then it will be combination of bits. Then it will be combination of bits. If I talk about the feature, na, n is the number of feature. Number of feature. N is the number of feature. You are having one feature, na, that is why it came 2 to the power 1 equal to 2. That is why you are using 0 and 1. If you take two features, na, then it will be 2 to the power 2, 4. Such combinations required,
Okay, sir.
according to what I understand. That is why I am multiple times saying the number of feature is more than he हो गया फिर तो.
Sir, what is the significance of state preparation?
Significance of
State preparation is there na before adding layers.
before adding layers, we do have
State preparation in that QML dot
state
amplitude.
parameters. Now we need to define the parameters with x. X is an input. So like x is an input, and we require the parameters weight and the bias, just like machine learning. Okay, because the tuning will be done for these parameters only. That is why it's saying state preparation. All right. And once in a superposition, it can have a multiple states. It can have a multiple states. So once we give 0 and 1 and doing transformation in variational circuit, now we are allowing for multiple states to hold or to exist. That is what it is saying in state preparation. So take input, convert it into multiple states by circuit. All right. And assign parameters to them. That is what it means. You can clearly see state preparation. All right, this is we are calling. Okay, so convert them into what? Amplitude embedding means probability amplitude. That means convert them into quantum superposition. That's state preparation. Because x cannot be solved, na? Your x cannot be solved unless and until it is not converted into quantum. You cannot solve it. That is why we need to prepare into quantum, then pass it to the quantum circuit. In quantum circuit, we are having this combinations. So state preparation, assigning the weights. Okay, you are ready with your classifier. That means input with weight and the bias. Weight will be random. Bias is zero. Error, accuracy, every formula has been present here. Run it for 100 times. Your result is in front. 98% accuracy. Taking this as a reference, I have done other code also. Breast cancer data. Okay, you can take wine data, breast cancer data, wine data. Again, very easy. The code is entirely same. Just change the data set. Okay. Then I have took digit data. Digit data also I have taken. All right. I train my model. Take the same reference. I got this much accuracy, 98.96 accuracy. Very good. Okay. And here you can see the predictions of the digits. Then things got changed, and I took another data set. Okay, that data set was MNIST data set because I want to switch towards complex problem. That we will discuss tomorrow, but I request everyone to run this notebook and try to understand again what I taught you. All right, fine. Try to understand again what I taught you because giving that much load of lecture, now you will get. We are preparing circuit, and I don't want to get short circuit. All right. Anyways, like how you felt for this today's session, because tomorrow also we are going to do take some data set and then apply over it. Meanwhile, this basic also again I will review, and then I will take a project based data set. I've mentioned potato. I can take any kind of data for classification as per research perspective, and I need your inputs. Did you understood quantum, like have like as I say, initiative I took for quantum? Is that okay? Any feedback or suggestion from your side?
Ye- Yes, sir. It is very informative, and means we learn terminologies like we never knew for that. So it is very helpful.
Thank you, madam.
Yes, sir, it is very good, sir. Starting from the basics, we have learned so much in this session. Thank you so much, sir.
Thanks a lot.
But sir, for images, it will take lot of
Obviously,
computation.
sir, that is why I'm saying, sir, features, because you need to extract the feature. And if you see my last code, what I was showing you, but I okay, what I did, I applied CNN, convolution neural network. That means first extract the feature, then I applied PCA, principal component analysis, further reduce the feature, and then apply neural circuit, this quantum circuit, not neural. Neural is the quantum circuit. So I am continuously reducing the features because size of the image is high and it will be difficult for you to work. Okay, because one more thing, this is simulation of quantum environment. I don't have quantum machine, sir. And I request everyone, if you are taking quantum as your research perspective, please, before taking any kind of research topic, you should be aware of what kind of data and what kind of resources I can use to solve that data, what kind of algorithm. If I don't have the resources available, then it is challenging. Anyways, research, this is good one. Okay, and government is investing in quantum. Fine. In coming time, it is having lot of scope. Lot of scope will be there in coming time. Can you turn on the camera, please, everyone, so that I can take the attendance? Or if you have any doubt, please let me know. I can stop.
Sir,